review it in your notes, review it in the book, was we protonated the tetrahedral intermediate. The cyanide adds in, we get a tetrahedral intermediate, negative charge on oxygen, that picked up a proton from HCl. Well, here, because we're exposing it to hydroxide, the hydroxide can grab the proton from the hydroxyl group in the cyanohydrin. If the last step in cyanohydrin formation is protonating the oxygen, then the first step in the reverse of that mechanism must be deprotonating the oxygen. So we get water as the other product of that proton transfer reaction. We've got a tetrahedral intermediate, which in the forward mechanism for cyanohydrin formation was produced when cyanide added to the carbonyl carbon of an aldehyde or a ketone. Well, that cyanide is going to leave. What causes it to leave? A lone pair on that negatively charged oxygen swings down, makes a pi bond. Here's how the acetone product formed. And we generate some cyanide, which I'm going to kind of write like this. Why am I writing it like that? Because now we can have the cyclohexanone get involved. Well, if you don't believe me that the steps that we just went are the reverse of the steps of cyanohydrin formation, guess what we got to do to get the other product? We got to make a cyanohydrin. We're going to have it all up in one mechanism, and you'll see how it's reversible. The cyanide comes in and it adds to the electron deficient carbon. And we get, voila, a tetrahedral intermediate. I'm not going to draw that CN triple bond anymore, not at all involved in the reaction anymore. So we get a tetrahedral intermediate. What do you think has to happen to get us the final cyanohydrin? It's got to pick up a proton. Well, in aqueous hydroxide, it's got to pick up a proton from water. So this is definitely a reaction we see. We certainly talk about cyanohydrin formation. Just we're kind of putting things together in a novel way, and we haven't seen anything quite like this before. But again, part of demonstrating and understanding organic chemistry is recognizing that the principles that you learn about regarding reactivity apply to everything. You just have to remember the pattern, and you can usually reason through a mechanism. The whole idea is you get further and further along in your academic career, real life, things aren't cookbook anymore. The point of kind of going to school, taking, upper division science and engineering classes is to kind of learn how to take all that information that you're thrown at from the books, put it together in new ways. Hopefully at some point you'll solve problems that have never been solved before. That's what we tend to do. Any questions? Let me do another one that's going to kind of reinforce what happens when we're in acid. So, recognizing whether you're under basic conditions, whether you're under acidic conditions, is really important because the pH tells us what charges are reasonable in the mechanism. basic conditions, negative charges are reasonable. Acidic conditions, positive charges are reasonable. This next one's a fun one. This is not one I've ever put on a test. But there's nothing unreasonable about it, and it's not even that bad a mechanism. This one actually involves 3 molecules of acetaldehyde. If you take acetaldehyde and expose it to acid, let's just assume we've got hydronium around, something rather interesting happens. We end up getting this cyclic product. Which happens to have the common name paraldehyde. Definitely, I would not expect you to predict, okay, 3 molecules of acetaldehyde exposed to aqueous acid, what's the product going to be? But that's not what a mechanism question is asking you to do. A mechanism question is saying, here is what happened. How did it happen? By understanding the principles of reactivity, the patterns are always going to repeat themselves, even if you've never seen it before. The patterns will still hold true. So let's see. We're ultimately, let's see if we can find the 3 molecules of acetaldehyde. Well, methyl group carbon bonded to oxygen, that looks like one of them. Methyl group carbon bonded to oxygen, that looks like the second one. Methyl group carbon bonded to oxygen, there's our 3rd fragment. Okay. Well, the question is, how did all of this come together? And all you got to do is expose acetaldehyde to aqueous acid, and you're going to get a little bit of this happening. Well, there might be other stuff happening as well, but we're going to worry about how this specifically happens. But let's talk about the really common pattern that we observed when we had acidic conditions. So now we have a cationic species. Aqueous acid hydronium, this is what is going to certainly be serving as a proton donor. Cationic species, is that going to be attracted to the electron deficient carbon of a carbonyl group? Positively charged species generally don't like other positively charged species. Positively charged species get attracted to things that are electron rich. What it all boils down to is electron rich reacts with electron poor. If you can find where the electron density is and where the electron density isn't, electron rich reacts with electron poor, you can start figuring out how electrons are going to flow. So what was the pattern that happened over and over and over and over again when we had a carbonyl compound acid? Well, how do we get to residence? We've got to protonate the carbonyl oxygen. And the reason why that's favorable is because we're going to get water. That's not so important. But the other product that we get is a resonance-stabilized cation. Following the arrows, following the electrons, all I did was I made an OH bond. And of course, I got my water. But this is a reasonably stable cation because it's a contributing resonance structure to a resonance hybrid. And again, this is going to become even more important in the third part of the course. You've got to recognize resonance, and I try to point out patterns. This is a big one. If you have a positive charge on an atom directly involved in a pi bond, you can always move pi electrons towards that positively charged atom, and that gets you another resonance structure. The reason why acid catalysts are often employed in these carbonyl reactions is because by protonating the carbonyl oxygen, it actually makes the carbonyl carbon an even better electrified. It basically enhances the positive charge density on the carbonyl carbon, which makes it pretty reactive towards nucleophiles. Now, there is one question in part 2 where I specifically want you to draw basically all of the important contributing resonance structures to an intermediate that happens to be a resonance hybrid. And it'll be very evident which question that is, because you will see, the boxes with the resonance arrows, and then furthermore, you're going to be telling me which of the contributing resonance structures is of relatively greatest importance. That's always an important consideration. These aren't equivalent. Having a positive charge on oxygen is definitely not equivalent to having a positive charge on carbon. Which of these two resonance structures is of relatively greater importance?
The second one.
Not the second one. Octet rule always predominates when we're judging relative importance of resonance structures. The reason why this isn't as important is because the carbon has only 6 electrons around it. Here, carbon has 8 electrons, so does oxygen. It's counterintuitive. You might think, well, carbon's less electronegative, but octet rule always predominates. The more important resonance structure is definitely the one on the left. Now, in the other mechanism problems on the test, there's one where it's even a separate question. It's basically, in this separate mechanism, you get a resonance hybrid. Draw me all the important resonance structures. Tell me which one's most important. In the other mechanisms, the way it's stated, and this is very similar to the old test that I posted. For you guys, it's going to be like this. If an intermediate is a resonance hybrid, it is only necessary to draw one of the contributing resonance structures. I'm not even going to ask you to draw me the most important one necessarily. You just got to draw one. So that means if that's the way it were phrased, you could give me this one, you could give me this one, really wouldn't matter. Now, later on, because resonance is so much more important for the third test, it's probably going to be stated if there's an intermediate resonance hybrid, draw only the most important. And you'll see why, because the mechanisms, if you think this stuff is complicated, you ain't seen nothing yet. Just wait until we get into chapter 19. It's just my favorite chemistry to talk about. I'm so happy we're almost there. Anyway, this is kind of the motif. Now, we're not quite, close to where we need big. We've protonated one of the 3 acid-aldehyde molecules that ends up in this product. Well, each of the carbons in the paraldehyde product, and that's just the name of the molecule, is bonded to 2 oxygens. This carbon is bonded to 2 oxygens. One came from the one it was originally bonded to, one must have come from another molecule of acid-aldehyde. Similarly, this one is bonded to a methyl group. It's bonded to an oxygen that must have been originally part of the aldehyde, and it's bonded to an oxygen that came from another molecule. Same deal with this one. So let's see. If we're going to end up having another oxygen come in. Let me draw this like this. Let me draw just the more important resonance structure. I just wanted to again make the point about the resonance. Well, protonating the oxygen made that carbon more reactive towards nucleophiles. Nucleophiles, best nucleophiles are anions. If you don't have any anions, having electronegative atoms with lone pairs is typically second best. If you can't have that, then, well, pi bonds work in a pinch. Well, remember, we've got to have 3 more, or 2 more, I should say, molecules of the acetaldehyde somehow get involved in this whole mechanism. So let's see, we activated, not every molecule of acetaldehyde that's in the system is going to get protonated. Just a little bit is going to get protonated, but as soon as that happens, there's going to be plenty of unprotonated acetaldehyde. How might a carbon-oxygen bond form between these things? Well, the electron-rich oxygen of a second acetaldehyde molecule can come in and donate an electron pair to the enhanced positive charge on this. Again, I'm drawing most important resonance structure, but this one shows that that carbon has an even bigger partial positive charge on it. So what's that going to give us? That's going to give us something that kind of looks like this. Let me do it like this. So we get an OH. This oxygen formed a bond if this electron-rich oxygen gets attracted to this electron-poor carbon, we end up with just a hydroxyl group on that carbon. We formed a new carbon-oxygen bond. We know that that had to happen at some point. We get this intermediate, which is a resonance hybrid. I'm not going to draw the other resonance structure. This is already the most important resonance structure. And what do you know? Well, now this carbon is going to be enhanced in its electrophilicity. So repeats. Have yet another it's basically the same thing we just did. Starts to get, when you're drawing the letters like I am, it starts to get, that's why we use the line angle convention. Will point out, I don't know if this has been an issue or not. Alicia hasn't said anything about it, so maybe that's a good sign. But if you're drawing the symbol C to represent carbon, then you do have to draw explicitly the H is bonded to that C. Okay, so this carbon still has a methyl group and a hydrogen. The line angle convention means we don't have to do that. And then we end up, let's see, this oxygen came in. It's still doubly bonded to a carbon, which still has a hydrogen and a methyl group. And now we're almost there. Now we're almost there because this can actually adopt a conformation. Let me put the lone pairs. This oxygen picked up a second lone pair. Now this oxygen on the hydroxyl group is actually not that far, or it can adopt a conformation where it's really close. 1, 2, 3, 4, 5, 6 six-membered rings, good in chemistry. So instead of just having this keep going, and that actually happens, you can actually make a polymer, just a linear polymer basically. You just have the oxygen on that original molecule come in, attack the carbon that is enhanced in its electrophilicity because it's doubly bonded to an oxygen with a positive charge, resonance hydrogen. Again, this is also a resonance hydrogen. So again, the point I'm making is this is a reaction that certainly we haven't seen before. Let me kind of I'm going to draw this now more like I drew the final product, just because it's a little bit easier. The only thing that causes this to be different from the final product is there's an extra proton. When this six-membered ring snaps closed, there's still a hydrogen on that oxygen, so that oxygen has a positive formal charge. This is not a resonance hydrogen. There's no pi bonds. What do we got to do to kind of get the final product? We got to lose that proton, and that's going to probably happen by having water come in and grab it off. Point is, even though I'm not even going to draw that, those are methyl groups, I'm just using the line angle convention. Let me get all the lone pairs in there. The pattern that we've seen over and over and over again when we protonated oxygen, when we kind of had this resonance going on, it makes the carbon even more attractive to nucleophiles. Well, you got this small acid aldehyde molecule, oxygen, coming in as a nucleophile. Well, now this end has a carbon. It kind of looks where this original acid aldehyde is basically acting like a big proton. It behaves much the same way, and then we don't keep going. You could, but that's not what we're trying to explain. Because you can close up a six-membered ring, which is reasonably stable. You get that original oxygen coming in, snapping that ring closed, and then you just pull off a proton. Acid conditions, cationic intermediates. Basic conditions, we have anions. When we're working under acidic conditions, we've got cations. Neutral conditions, then you're allowed to have both charges. But a lot of these reactions, either basic conditions, that's what we started off talking about, now we've moved into the acidic conditions. So, again, there is one problem on the test where it's a reaction that you've never seen before. Nothing that I've ever mentioned in lecture, but I tell you, here's what happened. And the questions kind of walk you through the mechanism. If you understand kind of the patterns, you ought to be able to come up with a reasonable mechanism that shows you how that reaction that you've never seen actually takes place. One more mechanism, and then we'll switch into synthesis. I'm going to show you again something that happens take this molecule, expose it to aqueous acid, you end up getting this. Let's see. Got to see how things change. First of all, where do you think the oxygen in the product must come from?
Water.
Yeah, you're working, aqueous acid, CH3O plus, you consume your water. So let's see, water must have been the source of that oxygen. What type of compound is this? We have a carbon doubly bonded to a nitrogen. Where have we seen those before? Because we've seen them. In fact, somebody threw that out as a suggestion for what the cyanohydrin was. Not an oxine. Oxine's got to have carbon doubly bonded to nitrogen, which has a hydroxyl group. This is just in. How do we make it in